All right, hi guys. Welcome back to Sarah's video recorded LGTs, I guess. So I just wanted to give a disclaimer. I'm not going over IV bolus in this particular lecture or this video. I'm planning on doing a different video that kind of goes through the math since it is a more math heavy portion. But for the rest of these, I'm going to go over block 1 of your PK. So here's the disclaimer again. So please, if you make good grades, tell me that I'm the one who made it possible. If not, then come to me for more tutoring. And then here's what we're going to go over. Once again, IV bolus, separate video. So don't get too concerned if it's not here. I'm just going to make a separate 5-10 minute video on how to work through a math problem. All right, so I'm going to start with Introduction to PK/PD. You've probably heard this a lot of times, either in undergrad or even now in pharmaceutics. So pharmacokinetics is what the body does to the drug. So that's your ADME, absorption, distribution, metabolism, elimination, or excretion. And then PD is what the drug does to the body. So I think of the dynamic starts with a D, drug starts with a D, so it's what the drug does to the body. And this is seen through changes in your heart rate, blood pressure, things like that. So what the drug is causing to change in you. In terms of drug concentrations, now, it's really difficult and, dare I say, impossible to figure out how many receptors are being worked on by a drug. And so we like to use an indirect measure through looking at blood, urine, saliva, plasma concentrations to figure out a correlation between how much drug you get and how it affects you. Now, kinetic homogeneity for completion, this is just a definition that might come up. So this is a predictable relationship between plasma drug concentration and the concentration at the receptor. So like I said, we can't directly tell how much drug is at the receptor, but we can try to correlate it to plasma concentration and then make assumptions there. Now, adverse effects are due to drug binding at sites that aren't at the receptor you want. So maybe, it's the perfect example for me is Benadryl. So it works at histamine receptors, but it could also probably antagonize muscarinic receptors or other receptors in your brain that cause sedation, and we don't want that. We just want it to help treat allergies, right? So unintended side effects could be sedation. And then the less specific a drug is means the more receptors it'll attach to and cause adverse effects. Now, specifically talking about pharmacodynamics, there are definitions here that you might want to be aware of for the exam. So Emax is basically the maximum effect of a drug. So if a drug lowers blood pressure, maybe the maximum it can do is 20 millimeters of mercury, for instance. So beyond that point, you're not going to see an increase. You're not going to see 25 millimeters of mercury decrease in that drug. Also, however, you could see more toxicity happen. So once again, we've got a drug in there. It could bind with other receptors, or it could just cause mass chaos, and you could get a lot of unintended consequences from having too much drug in your system. So I gave the example of blood pressure. You can lower heart rate, so maybe you're trying to reach a target of 70 beats per minute. And then for asthma, maybe you're trying to get a peak flow of 80%. So EC100 is the concentration, so C is the concentration, that produces 100% of the effect. So this is the concentration for somebody that'll get that 20 millimeters of mercury. EC50 means that how much of that concentration will produce 50% of the effect. And effect can also be called potency. You can mix and mingle those words. So if it's efficacious, it's potent. So that's how the drug will exert its effects, is by being potent or effective. And then tolerance is a reduced effect with repeated exposure. We hear about this with opioids. There are other drugs that build this tolerance in where the more you take it, the less receptive your body is to the drug, and so you need more of it to get the same amount or the same effect. So you can imagine that little S curve that you see with effects, and I think that's going to be on the next slide, but basically the tolerance will push the curve to the right so that the concentration you need has to increase in order for you to get the same effect. All right, okay, this isn't the picture I was talking about, but I can still use it. So yeah, if this curve pushed over this way, then that would be an example of tolerance. So tying that into therapeutic drug monitoring, there are some drugs that are beneficial to us, but they have a narrow window of effectiveness, and they could become really toxic really quickly if you reach a certain threshold. So we use therapeutic drug monitoring to make sure that if we have a drug that can benefit a patient but could be toxic and we want to make sure we get the right effect and concentration, we can monitor the levels in order to make sure that a patient doesn't suffer unintended consequences. So therapeutic drug monitoring is good for drugs that have a correlation between plasma concentration and response. That means that if we get the concentration back, we can kind of tell if it's working or not because it's within a sweet spot. It's also good if we have variable responses at the same dose in multiple patients. And I don't mean that is like a good thing. I just mean therapeutic drug monitoring is great for making like individual regimens for patients. So maybe we know the range that it works, but every time we administer the same dose to different people, they get different concentrations. So we want to make sure that we make it individualized to the patient so that we can get them into that optimized plasma concentration. And then, like I said, so dangerous drugs, toxic drugs, that would be a good thing to go on. If it was safe, we wouldn't really care about it because, I mean, if we could go, like, increase the concentration, and if it's not going to hurt them, then that's not a good candidate for therapeutic drug monitoring. We're looking for those dangerous drugs that we want to make sure patients don't suffer from. And then the last one is pharmacologic effects cannot be assessed by other means. So, like, we're really basing it off of that concentration we get back. And I already talked about safety, when not to use it, but also if you have a drug that has a lot of metabolites, that could skew the results, so that's not a good candidate. And then no defined therapeutic range, meaning like you get a concentration back and you can't tell like if it's going to be helpful or harmful, that's not a good candidate. We want something that we know the concentration and we know that it varies between patients, so we need to individualize it. And then the therapeutic range is the concentration that maximizes the effects, minimizes the toxicity. And just a little tidbit here is that boundaries are not absolute, meaning that like you can have drugs that have toxic effects at any level because, you know, bodies metabolize differently. Sometimes like the window is so like narrow that you could have like toxic and therapeutic effects at the same time, etc. And then here's like a little diagram of showing like the effect versus toxicity, and that this is a diagram to help you show you what the safety margin is. I believe that Dr. C, he also has a safety margin reach out this way, which is also valid because it'll be safe all the way from like this point basically and back. If you go beyond here, you're risking that toxicity creeping up and causing an adverse effect. So this is just like a quick little blast back to the past with math, just to let you know that the independent variable, if he ever asks a question about that, that's just the x-axis here. This doesn't change. And then the y-axis is the dependent variable, which will change. And I say change and don't change, it's just referring to what graph you're talking about. So concentration technically could be independent or dependent depending on like what context you're talking about. So just for general knowledge, x means, or like on this like horizontal axis means it's independent, and then on your vertical axis it is dependent upon this value here. And there are examples for your reference. All right, so now to my first question. I did intersperse them into here. I'm trying to think how I'm gonna do this. Yeah, I'll just like pause for 5 seconds and then like continue so you can like pause on your screen in order to get this. So first question, which of the following would be suitable for therapeutic drug monitoring? All right, so this one would be digoxin because it pretty much fits everything I was talking about. Not only is it like a toxic drug because it has like a narrow therapeutic window, which kind of gives it away, but also it has a predictable response to concentration. So we know that within a certain value, it'll have the effects we want. But if we go above that level, it could be toxic. Acetaminophen, it's kind of like relatively safe. We know that like 4 grams is the max, but we wouldn't do monitoring on a patient and like waste their money on APAP. And then I just made up this drug, but it might be toxic, but if it has varying response to concentration, meaning we don't know how a patient is going to react to it, then that's not really good for therapeutic drug monitoring. All right, so this is mostly FYI, and I say that with all these asterisks here. So next semester for neuro, you're going to have to know a couple of anticonvulsant ranges, but for the purposes of this class, for this block, you don't need to really know these. they're not gonna, I don't even think he's gonna test you on the ranges, but for future blocks, you might want to know digoxin and lithium. All right, so on to pharmacokinetics. Here are some more definitions for you to understand to be able to perform on the exam. So our Cmax is our maximum concentration. So that's going to be, I've got a diagram over here. So that is like the highest concentration your drug's going to get once you absorb it. So you absorb it and it like reaches a peak, and that's your max concentration. Tmax is the time at which you reach Cmax. Area under the curve is going to be like this thing. It's the area under the curve. And half-life is going to be the time it takes for a substance to reduce to like half its original volume, or like if you get it at a certain point and you get a concentration, how long it takes for it to reduce to like half that amount that you recorded. Elimination rate, this one you'll sometimes see it as just K, KE. This one is the rate at which a substance is removed, so it would be like, you'd calculate it like a slope basically. And then volume of distribution, I'll go over this in more detail because I think there's like a more specific lecture that goes over it, but it's the dose of the drug divided by the concentration at time zero, meaning when we, well, this isn't a good example, but when we administer it, and like imagine this like peak right here is over at this like t equals 0, we take the dose divided by that concentration, and then that's the volume of distribution. So that's how we, that it's not like the number isn't absolute, meaning that if it is a volume of distribution of 20 liters, that doesn't mean you have like 20 liters of it in your body. It's just a way to show like, is the drug staying in your blood more, or is it distributing to like fat more? And yeah, it's an apparent volume, it's not an actual volume. And then clearance is the volume of plasma that drug is removed per time. It's not the drug removed, it's the plasma being removed and how much drug is in that plasma. All right, and yeah, so here are some visuals for your reference if you need different ways to understand how to visualize everything. So we've got Cmax, max concentration, go down here, and that is Tmax. All right, so compartment models, once again, there's like another slide deck that has everything specifically, but the best way to do good on the exam is if it's one compartment, it's like one slope. If it's two compartments, it's got two slopes. And we'll go over it in more detail in a moment. All right, so in terms of elimination, I just have here how to understand the rates of elimination. So if it's zero order, that means that a constant amount of drug is being removed per time. So it doesn't matter how much drug is in your body. Like, let's say the rate is like 10 milligrams per hour. So every hour you're going to lose 10 milligrams, no matter if you have like 100 milligrams in your body, 50 milligrams, it's always going to be 10 per hour. Whereas first order, it's more of a proportion, like I'm going to lose 20% per hour. So like if I have 100 milligrams in my body at time zero, in 1 hour I'm going to have 80 milligrams because I lost 20 milligrams. And then you do 20% of 80, and then you do 20% of that, etc. So it'll be more of like the rate is like 1 over hour versus a like set amount. All right, and this is from one of my slides from the past. I want to say it was renal, but you guys weren't ready to learn this, but now you are. So this is like another way to understand the whole like large volume of distribution versus like smaller volume of distribution, and how like this is technically the blood, and then these are like tissues. All right, so clearance. I have some different equations up here for you, but so this is the one that Dr. Chattervidula is going to give to you, and then these are just like me kind of showing you how you can manipulate the equations if you need to figure out clearance. Like if you're not given the elimination rate constant, but you're given half-life, then you can still figure out what the clearance is. And then just for everybody's reference, just in case you didn't know, the natural log of 2 is this 0.693. I like natural log of 2 because it like, you know, keeps the whole number together. I'm not rounding off to 3 decimals. But you can do it whichever way you want. I just like the natural log of 2. And so this, once again, is the volume of plasma from which drug is removed per time. It can be elimination rate, not to be confused with elimination rate constant. That's the K value. And there's just examples of like how it might be reported, like liters per hour. And it's not the exact drug being removed, just like how fast plasma is being cleared. And then here's, once again, are all like the meanings of like area under the curve. So I remember on the exam, it asked me to find like the area under the curve of a drug, and I was getting so confused because I didn't remember learning an equation exactly that, but I was given the dose, the bioavailability, and the clearance, so I just had to go back and like rearrange this equation to figure it out. So don't try to solve calculus like I did for like 10 minutes. Please, like if you get an area under the curve equation, you might be able to like work backwards with this one. All right, half-life. Once again, this is the equation Dr. C gives you. But this is also a way to understand if you have, like if you don't have half-life but you have the rate constant, then you can once again manipulate the equation to get the clearance anyway. And so it's the amount of time it takes plasma concentration to reduce by half. And I just put there the relationship between K, or the elimination rate constant, and half-life. All right, so here is a question, like a math question, because you will be expected to just produce like half-life, elimination rate, etc. So I've given you volume of distribution, your half-life, what is the clearance? And I give you the equation which Dr. C will provide on the exam, like a whole list of equations. You just have to remember which equations to use. All right. All right, so I really wish I had like a board to write on, but for the purposes of this PowerPoint, I just like worked it out here. So I take, what I did was I basically switched half-life and clearance with one another, because you multiply it over to this side, you divide half-life back over there, and then you get this kind of equation right here. And then I plugged in all my values. I like ln2, you can use 0.693. And then I got 1.73 liters per hour. And be sure to check units. I don't think Dr. C's tricky on them. He's not going to like give you, I don't know, he's not going to try to give you grams and not make you realize that you have to convert it to milligrams, for instance. He'll let you know what values he wants. All right, on to one compartment. We talked about one line here. I think I actually made this graph. Cool. So the distribution and elimination are basically similar between tissues, meaning that I use the example, so let's say there are two people in your classroom, and then there are two people in the hallway outside of the classroom. So as the two people in the room are leaving into the hallway, two people in the hallway are getting out the door. So like the rate is like 2 people per whatever unit of time. So it's like evenly eliminating from the room to the hallway to outside of the building. And so you basically kind of consider this entire building as like one room, essentially, because everything is leaving in such a homogeneous way. Let's see, everything's happening instantaneously, and this isn't true. This, like, we're making an assumption, so obviously our body isn't just one compartment. It's not just like a hollow like system that intakes and outtakes, but it's some drugs can actually be estimated to have one compartment parameters, and so we can assume generally that like the rate is going to be like a homogeneous rate there. And then the KE, the elimination rate constant, is proportional to the drug decline in the body. So you can calculate KE from taking like a concentration here, and then the time between them. There we go. Now, two compartment is a little trickier, but it does reflect how many drugs work, because at first the drug is being absorbed into the body, and then although some drug might be eliminated, after absorption it's mostly distributing into the body. So whenever you have a sharp decrease in concentration here, that's actually the drug distributing to like all the tissues in the body, or the peripheral compartments. And then over here, once it starts like kind of, the slope becomes a little more flat, that's mostly purely elimination. That goes back to like the one compartment, the here. Let me see. So the essential compartment, these are like the areas that are highly perfused. So I'm talking about lungs, kidney, liver. Whereas peripheral, I like to think of it as like fat and muscle tissue for the most part. If it's muscle, it'll have myo. If it's fat, it'll have adipose. So myocardium is muscle of the heart, for instance. And then typically distribution is more rapid than elimination. So as you can see, you have a rapid decline in that distribution, and then elimination is a little more flat. And then here are just math terminologies. I think you just want to know the difference between like macro and micro constants for the exam. So macro constants basically describe pure distribution, pure elimination, whereas micro constants are like, I don't have the image here, but it's kind of like that interplay between going from the central to the peripheral compartments, going from the central down in out of the body, elimination. And if you combine those together, those should make like some macro constants. And just know that 2 compartment is bi-exponential, meaning it has like 2 different linear components in there. So we have like alpha here, which is actually this red line, and then beta. All right, and then I remember one question being on the exam regarding this figure, but it's going to be similar to like how your quiz was or your homework that had this, if not like something in class where he asked you to answer a question with this graph. But I kind of explained it already, but I'll go over it a little more. So 1 is basically the injection. So you basically added drug into your system, and it's like, we're just assuming it like absorbs 100% because it's IV, so bioavailability is 100%. And then it'll rapidly distribute into cells. So that's what this part 2 is it's distributing from the central to the peripheral compartment. And then 3 is going to kind of be like we're moving away from distribution and going towards just elimination. So it's kind of like distributing between that central and peripheral compartment. And then 4 is just like pure elimination. That's your like beta slope there. And then so just recall that when you are calculating like a half-life of a drug, you're actually looking at this final elimination. You're not looking anywhere up here where distribution is still taking place. And then so here the rate is going to be like beta, not like a micro constant. So that's why I have this equation right here for you. And then a diagram next to it to show like we've injected it, it's being distributed, and then it like slowly gets eliminated out. All right, so here are some more questions. So vancomycin follows 2 compartment model kinetics. So a distinct distribution phase lasts for 2 hours, and then terminal elimination starts. Then a patient was given a loading dose for 2 hours, and concentrations were collected at 0.5, 2, 6, and 7. Which of the following are the best to use in the calculation of half-life? And whenever I say loading dose, that means like short infusion. So we basically administered it like as rapidly as possible. We weren't trying to draw it out. We're giving them like a bolus in a way is what I'm trying to say. Oh no, okay, sorry. All right, so the answer here is 6 and 7. So I think you received a similar question in class, or I think it was in class. So basically, if it distributes over 2 hours, if we collect it at the 2-hour mark, it might still be distributing in the body depending on the patient. So it might not be good to use that because that might still be around 3 here. We don't know for sure if it's pure elimination. So you always want to go with like what's after that distribution phase. So in this case, 6 and 7 are the ones that end up after that 2-hour mark. So those would be acceptable. All right, so which of the following is true about this graphic here? All right, so in this case, 4 shows elimination here. So like we said earlier, so this is elimination. This is where like distribution is just about finishing up. Here we're like rapidly distributing. Here we've just injected into the body. So you haven't completely distributed everything. You're waiting to distribute around here. At 2 is, I think I might have, it's not just in the central compartment. Although this shows like what the central compartment is doing, technically that drug is going into the peripheral compartment. So that's what that means right there. And then peak absorption occurred probably at 1 when we administered it. All right, so speaking of absorption, We're talking about drug molecules passing from your route of administration, so whether it's an injection, oral, sublingual, eardrops, eye drops. How is it getting into our bloodstream, basically? So we have different barriers that we have to overcome with that. So anything ranging from our physiology, meaning like our gastric acid content, our epithelial cells and how well they'll allow passage of different molecules, transporters, like if it's pushing it in or flushing it out. And then even the drug itself can have different formulations that will change how it's absorbed. So maybe it'll get absorbed in the small intestines, maybe we want it to absorb elsewhere, like in the colon. And then here is like another way to look at the different effects of different factors that change absorption of different molecules. So over here, drug absorption. So maybe the drug just never gets absorbed at all because it gets formulated in such a weird way that the body doesn't accept it and it gets excreted immediately. Or sometimes like the pH, like maybe your gastric acid wasn't acidic enough to dissolve it, or maybe it was too strong against like small intestine pH to be able to break open. Over here we have the gut wall. So maybe you have like a PGP enzyme that's like pushing that drug back out. Sometimes you might have a drug that doesn't normally get in, but you have OATP here, which actually like actively transports a drug into wherever it's trying to go. The liver, of course, is going to metabolize, and it has like phase 1 and phase 2 metabolisms. But sometimes that drug can get in, it might get like metabolized or maybe not, but you'll have different like enzymes and transporters that push it back out through the bile and go through enterohepatic circulation, which is what the EHC is. So it'll come back and it can either go back down and get eliminated or maybe reabsorbed all over and over again. All right, and to continue the different mathematical considerations of absorption, so we have to consider bioavailability. Not everything is going to be absorbed 100%, so we need to make sure that we know how much drug actually makes it into the bloodstream. So if it is oral, it needs to pass through both like the gut, and it has to either survive or work with the liver in order to get absorbed. For pH, once again, here are some like pHs that can affect absorption. And then I have a little chart here that I tried to make showing like if it's a weak acid or weak base, what kind of pH will it be non-ionized in? And if it's non-ionized, it will pass through the cells a lot easier than if it was just ionized, so it would like bounce off. So usually like a weak acid will be non-ionized at like a low acidic pH, weak bases at like a higher pH. And then lastly here I have CYP enzymes. So as we know that they can metabolize different drugs. And first pass is like a very significant process with oral absorption because it can potentially degrade your drug and make it useless. So we want to make sure that we can either pass that with enough drug to be able to reach systemic circulation, or we could make a prodrug that gets cleaved by CYP enzymes and becomes active upon metabolism. Transport proteins, I brought this up a little earlier, but we've got two big ones. I just want you to remember OATP and PGP. One pushes drug in, the other pushes it out. And this is generally true for all of them. The one little tricky thing about these two enzymes, you don't need to know it for this block, but I believe you need to know it in the future at some point. Or maybe you already learned about it in genomics, but in these hepatocytes, OATP can push a drug into the cell, but PGP will push it out, but not out of the cell, but into the bile instead. So what happens is a drug can get, pushed into the liver through OATP, it can get metabolized somewhere around here, and then PGP will further just push it out into the bile. Other than that, everything's kind of like more straightforward where we have PGP. The arrows are just pointing to like this tiny text, and I have like a slide or the next slide that shows it a little bigger, but if it's PGP, it's being pushed out, and if it's OATP, it's being pushed in. And here are the different diagrams to help you visualize it a little better. So like here's like a more comical one, and here's like the liver, kidney, and then the small intestine, large intestines here. But same process. So here's where the arrow is like pushing out if it's PGP, OATP is being pushed in. And just remember that like OATP can bring a variety of drugs, not just, I want to say that was like anionic, but it can bring like a lot of things in, not just anionic drugs. All right, so question. A patient is currently taking atorvastatin, which is transported into hepatocytes via OATP for metabolism. They were recently prescribed clarithromycin, which inhibits OATP. What do you expect will happen? All right, so for this one, we're going to have not only does atorvastatin increase in the serum concentration, but remember the serum concentration, that's in your circulation. So if you have more in the bloodstream, it can actually exert more effects, so it can actually become more toxic if you have too much of it. So that's why this is A and C. It won't increase in the hepatocytes because if we're inhibiting OATP, we're basically not allowing it to get into the hepatocyte. We're keeping it inside like the circulatory system. All right, so GI motility here. So gastric emptying is basically the time it takes for the stomach to empty into the small intestine. So faster means it gets from the stomach to the intestine faster. If it's slow, GI motility, that means it's not getting there as quickly. Food, just know that it can increase or decrease absorption. And you're not going to be asked, like, what does soda do or what does this food do? You'll be given, like, a situation and it'll kind of explain the process of what the food is doing to the GI, basically. And I have examples here, but once again, like, this is one of those, like, situations where if you're given a question about it, you'll be given the context and be able to, like, deduce what's going on. All right, so area under the curve. So this basically shows, oh man, that should be extent with a T. It's the extent of absorption, how much gets absorbed and how much effect it can have. And I have a little graph here that basically shows like what F is. So it's the area under the curve of oral versus IV. And if you can see here, oral is going to be like smaller than the extent of absorption of IV. And so if you divide these, you're always going to get a number that's less than 1. So it'll be like a fraction or a percentage of availability. In terms of rates, a faster absorption rate could result in a higher peak. So A has a faster absorption, as you can see, it like peaks a little more. This could sometimes be good if we just want it to like reach a certain concentration and then peter off, but sometimes we want to keep it in like a sweet spot because if we go too high, it might cause like a toxic effect. Versus, as we can see here, with B, it doesn't reach that toxic effect, but it still reaches like a therapeutic effect right here. If it has a slow absorption, it might not get to that peak that we want to be able to get to therapeutic effect. So C wouldn't be a good option to treat whatever condition it is indicated for. And then here's an example of, I know you're given this in another slide or during class. I think you will have a test question on this, and I just wanted to kind of like show you the comparison of like how to interpret these values here. So if Tmax is shorter, that means it takes a shorter amount of time to reach maximum concentration. So it'll basically absorb a little faster, and that's also indicated here with the absorption rate constant, as opposed to elimination rate constant, which has an E for elimination. This is actually the rate at which the drug absorbs. So I would like to show you, so the bigger this rate of absorption is, the faster it absorbs. So imagine instead of being like hour -1, just be like 0.417 per hour. So it's more per hour than like 0.2, for instance. A lower Ka means it's a slower absorption, so it's not going to absorb as quickly. And then AUC is the extent of absorption. So if they're the same, you'll have the same extent. If you have a higher number, there's like a larger extent of absorption. And if it's smaller, it's going to be a lesser extent of absorption. The biggest ones you want to know for the exam are like AUC and rate of absorption. Maybe time as well. But definitely these two. Oh, and here's the question. So refer to the table. So which of the following is true of these guys right here? And I have the absorption rate constant and then the area under the curve, or the extent of absorption. All All right, so this one is going to be that drug A is absorbed faster, as seen by we have more per hour being absorbed, and then a lesser extent than drug B because the AUC is less than that of B. The other two are like saying the same exact thing, just in opposite form. All right, so on to metabolism here. So we've got different types of biotransformation, phase 1 and phase 2. And you've probably gone over this a lot of times, so I'm just going to summarize it as phase 1 are usually the chemical reactions, so oxidizing, hydrolyzing, and then CYP enzymes are in phase 1, so remember that. Because CYP enzymes, they like to demethylate or they like to oxidize. They do kind of similar chemical processes just with an enzyme. Phase 2 is more like you're adding a molecule to something, you're conjugating it, you're putting like a kind of like a glucose-like molecule on it, you're putting a sulfur group, a acetyl group, things like that. And then the ultimate goal of both of these is to not only make the drug more soluble, but also make it more excretable as a result. Does this always happen? Not necessarily. Sometimes the body's trying to do a good thing, but the drug just like becomes less soluble and stays in the body. But the ultimate goal, the reason that they're doing all these things is in general to make them more excretable, to get rid of these toxins. In terms of non-CYP mediation, I believe you do want to know monoamine oxidase like MAO-A versus MAO-B. In terms of flavin and esterases, I can't remember a whole lot being tested on these. I just put this in here for completion. But if you recall, prodrugs actually have esters on them to help make the drug stay in the body more and to be more stable against different processes from being inactivated. So esters get hydrolyzed in order to either be metabolized if it's just a regular drug or to be activated if it's a prodrug. But the difference between monoamine A and B are listed here. I think the biggest thing is you're going to learn this a lot in neuro and you'll be like, oh, that's why we have to know these enzymes. But MAO-A, actually, if you inhibit it, it can actually cause hypertensive crisis because you're inhibiting the degradation of tyramine, which is kind of like epinephrine. They're like catecholamines that can raise blood pressure. So if you're not degrading or breaking down tyramine, you're actually increasing your blood pressure. You can cause like a severe hypertensive crisis. And you can find tyramine in cheese, wines, basically, you know, good stuff, or yummy stuff rather. MAO-B, however, it's a little better if you target that and use drugs to inhibit that. You're actually going to help with Parkinson's and Alzheimer's because you're affecting like dopamine production here, especially for Parkinson's. So the less you degrade dopamine, the better your outcomes for Parkinson's will be. And so that's the clinical significance of these enzymes. So basically MAO-A is bad, MAO-B is good. To inhibit, rather. All right, so I'm sorry if you can't read these, kind of small, but you will be getting the copy of the PowerPoint, and so you'll be able to zoom in or print this out if you need to. But these are all the different substrates that were bolded or put in red in the PowerPoint, and so these are the ones that are possibly testable. I organized it by the substrates, inducers meaning like which chemicals will actually increase the rate at which an enzyme breaks down drugs, and then inhibitors, which ones will stop that enzyme from breaking down drugs. And I've got little mnemonics here, so 1A2, for instance, it works with all the C's. C for caffeine, cigarettes, cruciferous veggies, char-grilled meats, they all start with C. B for Ben, because you've got bupropion, efavirenz, nevirapine, so BEN. But I think the ones that you want to pay most attention to are going to be 3A4 and possibly 2C19. I want to say you'll definitely have to deal with 3A4 because you're working with statins. There they are. And also ketoconazole, or these like azoles here, are inhibitors. I don't think rifampin was actually on or bolded in red on the slides, but that's like a hallmark. Like if you hear rifampin, you think of like a CYP inducer. So that's why I put it there for completion. But yeah, definitely no 3A4. Like I said, maybe 2C19 because of those proton pump inhibitors and clopidogrel. So yeah. All right, so phase 2 metabolisms, these can occur either by themselves or after phase 1. They might also be able to occur before phase 1, but there aren't any like studies that I saw that like showed that happening, but just know that it can occur by itself. It doesn't have to follow phase 1. So you have these two different ones, glucuronidation and NAT, N-acetyltransferase. And then the biggest thing you want to take away from this is that UGTs, there are 4 different families. Atazanavir is a substrate of UGTs. And then for N-acetyltransferase, we've got what I call D-SHIP, so dapsone, sulfonamides, hydralazine, isoniazid. And then the only other little nuance is that, where is it? So for isoniazid, the efficacy is not significantly altered by the rate of acetylation. I honestly don't think he tests on this, but this is like a really good slide to just like remember that different drugs get metabolized through non-CYP mediated reactions as well. All right, so speaking of, which of the following is a phase 2 reaction? All right, this is glucuronidation. So like I said, the different chemical processes are phase 1, and then CYPs are also phase 1. So glucuronidation is the only phase 2 right here. All right, which is true of combining a statin with ketoconazole? All right, so this one is going to be C. So both of these are metabolized by 3A4. Ketoconazole is a CYP3A4 inhibitor, and because it inhibits CYP, that means that that enzyme won't be able to degrade statin as much. Therefore, the statin will increase. All right, so we're on to elimination here. So from here on out, there might be a lot of slides with a lot of equations. I just figured if you want to understand why equations are the way they are or how you can manipulate them, I put that in here for your reference to figure out like, oh, how can you get from clearance and like these values all the way back down to figuring out a half-life. So these are here for you to look at. If you have questions, let me know whenever you see me. So elimination is an irreversible loss of drug from the site of measurement. In other words, you can excrete it through elimination or urination, through bile, like so your feces. You can sweat it off sometimes. You can lactate out drug. So it's just removing it from your body. So I've got renal and fecal there, but there are many more. Metabolism. You can convert drugs to either like active or inactive metabolites, and then these will eventually be excreted as well. So renal, hepatic, and gut, those could either go down fecal or maybe hepatic down to renal. And most drugs follow first order elimination, meaning it's a fraction of drug per time that's being eliminated. It's not like a constant amount. And I just have here, clearance does not alter volume of distribution and vice versa, just because you might have an assignment in the future where you are given like a table and you have to figure out like, okay, how does this parameter affect this one? So clearance and volume of distribution, they're like independent of one another. So just because you clear something faster doesn't mean its volume of distribution is going to change. So the rate constant, that Ke, is, here's the math equation here. And I just wanted to show you that if you take the elimination rate constant and you write it out in basic mathematical terms, it kind of looks like a slope equation, y2 minus y1 divided by x2 minus x1. And then this slide took me a while because I was like, wait, why is it C1 minus C2 rather than the other way around? But if you're wondering the same thing, it is because we just want our value to be a positive number or like an absolute value. Because you can see the rate constant is technically negative because it is trending downwards. But for the purpose of saying what is the rate is like a whole absolute number. And then I've got an example of how to calculate it with this little graph right here. So we take C at time 0 divided by C at time 2, and then take the natural log of that, and then we divide it by the time difference here, and then you'll get like a value that is like the inverse hour, or like 1.39 per hour. So terminal elimination, like we said, it's kind of like when we get this like beta slope here. and it's just elimination for the most part. Like absorption and distribution right here basically have already occurred, so we're just solely removing it from the body. And usually we determine this after just a single dose, because if you try to dose something afterwards, your absorption and distribution will come right back up and you'll get like more of like a zigzag pattern on your time versus concentration curve. And then this is just for completion, but there were just some studies showing that gemfibrozil might have different elimination rates just based off of what kind of machines you use to measure the elimination. So if you actually measure it for longer than, I want to say, was it 12 hours? Beyond 12 hours, it'll show a different elimination. And then vancomycin, although it's 2 compartment, we treat it like a 1 compartment and just wait for it to get to pure elimination and then calculate the elimination rate from there. All right, so refer to the table, and I've got all these parameters to calculate. I put down the units that I wanted as well, and then these equations would be given to you on like an exam sheet. All right, so for the elimination rate constant, I just took the concentrations, divided them, took the natural log of them, and then the difference in time is just 1 hour, so I got the rate here. For half-life, I just took that number and just put it in, like plugged and chugged for the half-life. For dose, so I gave you the dose up here, and I wanted you to extrapolate that the concentration at time 0, I gave that to you here, so this is the value you would use here. So we get the units in deciliters, but I said I wanted liters, so I just did a quick conversion there. And then lastly, I took the clearance, and then I took my rate times my volume of distribution and got the clearance here in liters per hour. All right, so clearance concepts here. So once again, for the 3rd time, removal of drug from the volume of plasma. And you have different ways to clear. And then here's like another equation. So the clearance is the dose divided by the AUC. You can like rearrange that however you want, but clearance can also equal these 2 values right here. And you can report it in blood sometimes if blood's like an easier way to report it versus plasma. All right, so if you're a well-perfused organ, then you might eliminate drug better or more efficiently than like a less perfused organ. So here are a bunch of graphs that I'm hoping I'll be able to explain extraction ratio to you. So extraction ratio is an organ's efficiency at removing a drug. So if a drug passes the liver, how well can that liver like take up that drug, metabolize it, and get rid of it? Or like the kidneys, how well can kidneys get rid of drug? So if it's a low extraction drug, there's going to be a ratio that's under 0.3 that is influenced by protein binding and intrinsic clearance. So what I mean by, 0.3 means that you can only remove like 30% or less of the drug, versus a high extraction drug means that you can like remove about like 70 or more % of it. And then medium, you don't need to know the middle between 0.3 and 0.7. It gets complicated because it's not purely like perfusion rate or protein binding or intrinsic clearance that determines the elimination of a drug. It's like all of them. We just make generalizations about like, oh, protein binding changes, therefore we're going to increase clearance or decrease clearance, etc. So here I have the image from the slides that you were given, so liver or kidney. So we have concentration going in, and then this is like the kidney or liver removing the drug, and then we get like a little bit of drug coming out. So your extraction ratio is going to be this amount that was removed, how much did we remove, divided by the total that we got to begin with. And so that's why this is always going to be less than this number, so you're always going to get a fraction that's less than 1. So we have 0.3, 0.7. I don't think you're ever going to get like 1, like a drug isn't like 100% cleared by anything. I mean, there might be some little nuances, but for the most part, it's always going to be like a fraction less than 1, never over 1, is what I'm trying to say. And then I also have diagrams here I found. So if it's a high extraction drug, and it goes through like this highly perfused organ. So that means we're going to get rid of a lot of drug and eliminate it out of the body. Versus low extraction, it might, kind of go into the hepatocytes, but for the most part, it's going to depend on how well it gets removed from the protein that it's bound to. And then intrinsic clearance is like its ability to be cleared without any help from an organ. So it just like decides to eliminate itself. All right, so I know this is a busy slide, but once again, this is for people who want to kind of understand like how to take equations and correspond them to other equations. And so I tried to draw this out the best I could. I've got the different values of perfusion, and then H stands for hepatic, so perfusion to the liver. If you see like R, it might be renal. Fraction unbound, FU, so how much drug is like not attached to albumin or other protein. And then the intrinsic clearance is CL, and then I, or CLINT is another way you can describe it. You'll see CLINT a lot more in your PowerPoints. So if we look at the liver solely, clearance is defined as the perfusion through the liver times the extraction ratio. So how well that drug is extracted from the liver and removed. And then you're also given the extraction ratio equation. So basically, if we take this perfusion constant, or not constant, but perfusion parameter here, and we put it, and we multiply it by ER, so we just basically put it in this equation. So that's what that Q is right there. That's QH, basically. And so this is the entire equation. These two equations, this bottom one and this top one, are the exact same. I just took ER and expanded it out for you guys. Now, the total concentration is going to be defined in different ways, either IV or PO. Recall that if it's an oral drug, we have to worry about bioavailability because it's not 100% absorbed. So that's what this F is here. So the POs are going to have like big F, bioavailability, in there. If it's an unbound drug, we have to think about just the fraction that's unbound. So that's why the unbound concentration has FU in the equations, whereas total concentration, it doesn't care if it's bound or unbound, so you don't have that changing up the equation up here. And then SS stands for steady state. So like if the drug is like in like homeostasis within your body, how is it acting, and how do these different parameters affect the elimination rate? And here I've like said the same thing just in case you look at the slides without listening to this lecture. All right, again, so here's math. I'm not going to go over this in detail. I just wanted to show you why you could make generalizations about high extraction being equal to the perfusion of the organ, and then low extraction being determined by FU and then the intrinsic clearance. I can't explain it too well. If you're asking questions, just understand that there's a calculus process, a mathematical process that makes these statements true. And if you need help, I can probably find like an undergraduate professor who could tell you why these statements are correct. But yeah, so this is for your reference. And so I've got some basic trends here. Oh, I forgot to say, you can just skip to this slide here if you just want to hear how to solve the questions without even having to understand the equations. But if you want to understand how the equations correlate to perfusion and protein binding, here's where you want to be. With protein binding, there are different trends. So if the protein binding of a drug decreases, that means that the drug is removed from, I keep using albumin because that's a classic example, but the drug is released from albumin and the total plasma concentration will decrease because now that free drug is free to be eliminated, but the unbound does not change. I know this is kind of like tricky, but if we look at the math here, what happens is if we can look at like IV steady state, and we take this hepatic clearance and we assume it's a low extraction drug, meaning that we can say that the hepatic clearance is equal to FU times intrinsic clearance. We can plug that in here, so hepatic clearance, that, and if we decrease this value here, we're basically decreasing the denominator, which increases this entire, oh wait, hold on. when that decreases, it increases. Oh yeah, so this is for total. Sorry, I almost confused myself, but yeah. So for total plasma concentration, it will decrease. Versus if, here, hold on.